and welcome everyone to today's session of Seminario Flotante. I'm very pleased to introduce Isabel Muller from Imperial College in London, and she will be talking about Polish groups and model theory. So thank you, Isabel, for accepting the invitation, and the screen is all yours.
Thanks a lot. Let me first share my screen. This is it. Yeah. So yeah, thanks a lot for the invitation, Dario. I really would have hoped that I could be there in person. This was the plan, but you know, the pandemic canceled more than just this plan, I guess. So that's fine. A small apology in advance. I thought I found a very sneaky way to give a Blackboard presentation and still saving time, but it seems that my computer didn't like the way, so it kept crashing. So I had to spontaneously create some slides of the first two parts. So that might probably be typos because this was very last minute. So I apologize for this. And yeah, now let's just get started, I would say. Please just ask questions as long, like whenever they come. Okay, so as Dario said, I want to talk about Polish groups and model theory. The idea is that I first give a little bit of background, so we all have the same level of notations. And then I want to give an overview of two aspects. First, the connection with stationary independence in structures and their automorphism groups. And then I want to talk briefly about a recent result about Polish structures. Just, okay, there's, yeah. Just to have a setting for the talk, we will fix a countable language L, and M will always mean a countable L structure. And by K, we denote a countable class of finite L structures. All this is unless otherwise stated. And we want to talk first about a famous Polish group popping up, which is the automorphism group of M. So it is a fact that whenever M is countable, its automorphism group is actually a Polish group. And this topology, this Polish topology, is given by the following basic open sets. Whenever we fix a finite partial isomorphism U, then we define the basic open sets defined by U as all automorphisms which extend U. So this defines the basis of the topology, which is Polish. And the leading question people around the area try to study is, how do now model theoretic properties of M impact and interact with topological and algebraic properties of its automorphism group as a Polish group or also as an abstract group. And there's a lot of very rich interaction. I want to focus on two things today. I first want to give an overview of how we can study the automorphism groups when we are dealing with homogeneous structures, which have a notion of a stationary independence. And then I want to talk about Polish structures and a recent result with Shaha Oriel, who is the student of Itai Kaplan, master student. Let me just recap, because I wasn't sure if everybody is model theorists, what omega categoricity is and what the famous Rühl-Natzewski theorem gives as equivalent characterizations. We say that M is a structure M is omega categorical if and only if it is the unique countable model of its theory. So if its theory has exactly one countable model. And then the Rühl-Natzewski theorem says that this condition is equivalent to the fact that the automorphism group of M is oligomorphic. So it has only finitely many orbits on each power of M. This is the first interaction that one can see, basically, where a model theoretic property interacts with a group property of the automorphism group. And another characterization that we will need later on is that it is omega categorical if there are only finitely many n types over finite sets. If you don't know what types are, ask, or maybe just think of them as orbits under automorphisms which stabilize the parameter set. As we're dealing in homogeneous cases, this will serve. I also want to quickly recall Frisé limits and strong Frisé limits. First, let's define what a Frisé class is. So we said always K is a class of finite structures. And we say that this is a Frisé class if it has some nice properties, which are the heredity property, meaning it's closed under subsets, the joint embedding property, That was muted me. Now I'm unmuted. Did you want to tell me something with that video?
No, I wanted to accept somebody, and then probably you accept the person, and then you just clicked into this. So I'm gonna accept the people that arrived, just so that that doesn't happen again.
Good. It sometimes just pops up, so I click it so that it disappears from the screen. And the most famous property of a Fresnel class is the amalgamation property, which I want to quickly recall so that we all know what it is. I did not manage to draw a nice LaTeX diagram in time, so let's do it here. So the amalgamation property says, assume we have structures A, B1, and B2 all in the class K, which has the amalgamation property, such that there are embeddings from A into both B1 and B2. Then there exists a C, also in the class K, such that together with embeddings of B1 and B2 into C, such that the diagram commutes. So whoever has done a little bit of Fresnel theory, they may know this back and forth. And we also had always this notion of strong parenthesis, strong Fresnel class, strong amalgamation property. What this means is sometimes our structures come along with the notion of strongness or closedness, which then substitutes in all the notions the normal inclusion. So for amalgamation property, this would mean whenever A is closed in B1 and closed in B2, then there exists a C in the class such that we can closely embed B1 and closely embed B2 into C. So this is just a version, which we will need later on. This is why I want to introduce it here. But let's get back to the slides. So this is a Fresnel class. If it has these three nice properties, and then some other notions we need in the Fresnel theory is the notion of the H of a structure. So for an arbitrary structure, we can denote the H by all finite subsets up to isomorphism. And we can also talk about the strong H if we have this notion, which then just means not all the subsets of M, but only those which are close to M. And another important notion is the one of homogeneity. And this means we say that M is homogeneous if any finite partial isomorphism of substructures extends to an automorphism of the whole structure. And once more, if you talk about the strong case, then this only holds for the strongly embedded substructures. And now the Fresnel theorem, which is the basis of a lot of constructions we did, and the refutal, I guess it's the word, of a lot of conjectures, is the one that the class K is a Fresnel class, or strong Fresnel class, if and only if there is a unique countable structure M such that the H is exactly K, which is in addition homogeneous or strongly homogeneous. So this is just a quick recap. Now let's go to the first interactions of the Polish automorphism groups and the model theoretic properties of the structures. In particular, in this part, we want to study the normal subgroup structure. And we will just fix that now we have a Fresnel class K given, and M will be its Fresnel limit. We want to see that very often actually homogeneous structures tend to have essentially simple automorphism groups, or at least automorphism groups where the normal subgroup structure can be well understood. Some examples for this are the pure set, where the automorphism group itself is not simple, but it is simple modulo those automorphisms which have finite support. And other Fresnel limit or homogeneous examples are the random graph and the random tournament, which both also have simple automorphism groups. Starting from examples, people have tried to kind of find general tools and general statements to capture whole classes of homogeneous structures and to describe the normal subgroup structure. And for me, like it basically culminated in the paper of Katrin and Martin from Katrin Tent and Martin Ziegler from 2012, where they introduced the notion of a stationary independence relation, which generalized several thoughts, like for example, of Laskar or of Katrin and Dugald to study these objects. And this is this notion we want to introduce now. So we start with this symbol, which model theorists we all know, it's like an independent symbol. And like this is a ternary relation between finite subsets. And we call it a stationary independence relation. If it satisfies several properties, I don't want to go into all of them. So it should be invariant under automorphisms. It should be symmetric and monotone. I want to explain a bit more in detail the last two properties it needs to satisfy, of which the first is existence. So we want for all finite subsets A, B, and C, and M, we want to be able to extend the type of A over C independently from B. What does this mean? It means for all these sets, there exists a copy of A over C, so an A prime having the same type as A over C. This is how we write it, such that A prime is independent from B over C. We can move it in an independent way. And the name-giving property, so hence the probably most important one, is stationarity, which means, okay, we know we can extend types independently, and stationarity says there's one and only one way, which means as soon as we have two sets having the same type over C, again, if you don't like the notion type, just think of it as orbits over C, having the same orbit, and both are independent from some other set B, then actually they have the same type over B and C. So there was a unique way of extending this type independently. This is the independence relation. And this is the small lemma giving a first interaction, which actually I wanted to prove, but I guess I'll keep it for later if we have time. As with the restructuring, I'm not sure how quick it goes. And the lemma says that if now we have an homogeneous structure, countable of course, which has stationary independence relation, then its automorphism group has a dense conjugacy class. So here we got a model theoretic property of M, and we can conclude of it a topological property of its automorphism group. That's the first example. So it's proof on paper, maybe in the end, if we have time. Now, here's the general tool. Again, as a reminder, the stationary independence. And the main theorem that Katrin and Martin prove in their paper, where they introduce the notion, is that assume now a structure carries the stationary independence, and we have an automorphism which moves maximally. I'm not defining here explicitly what it is, because I rather want to focus on consequences, but there's some notion defined with this relation. Then no proper normal subgroup of the automorphism group of M can contain this automorphism. Meaning, for example, if we could show that for some automorphism group, every automorphism moves maximally, then this has to be simple, because there cannot be any proper normal subgroup. This has been used a lot in many different directions. I want to name just some examples of applications. The first is in the same paper where all the notions were introduced, where Martin and Katrin showed that hence the isometry group of the Urysohn space, which is the completion of the Fresnel limit of finite metric spaces, is simple modulo a very well-known normal subgroup, which is the normal subgroup of bounded isometries. A result from before, but which also follows directly from the tools developed in the paper, is of Dugald and Katrin, which says that whenever we have Fresnel limits as above, where the amalgamation is explicitly nice, which is the free amalgamation, then they have simple automorphism groups. Actually, one has to exclude the pure set, but this is the only case.
Isabel,
Yes?
is free disjoint, or is it a little stronger than that?
Yes, it's a disjoint with no relations between the disjoint parts. Yeah,
okay, thank you.
Exactly. Thank you for the question. And later in 2015, David, Evans, Zanyagan, Nezat, and Katrin showed that the ab initio structures of Grotowski also have simple automorphism group, and there they had to extend the result to the setting of strong subsets. And also Zanya and Katrin, which this has been much before 2020, but when I went to archive now, this was the last version, so I put this date here, but they showed that they applied these tools to show that the automorphism group of generalized polygons, which Katrin had constructed, have also a simple automorphism group. And thereby they constructed the first examples ever of non-algebraic groups simple non-algebraic groups with a spherical VN pair. And this, the existence of them had not been clear before. So we see how these model theoretic tools can actually really produce some very nice groups with interesting properties, even outside model theory. Okay, so now we want to see some generalizations of this tool. One really helpful property is the symmetry, but as helpful as it is also very restrictive. So people have been working around it to generalize it to other settings. One of these generalizations from Itai and Pierre in 2017 has been the definition of a canonical independence relation, which shares some properties, but it's a little bit like a generalization. And what they showed, this should appear after, is that if we have a homogeneous structure with this slightly weaker notion, slightly different notion, then still the automorphism group has a dense conjugacy class, and this is even a cyclic dense conjugacy class. Last year, Yibei Li, the student of David Evans, she defended last year, also made a generalization, a non-symmetric generalization of these tools. She introduced something called a weak stationary independence relation, which has all the same properties except for symmetry, but then all the properties, she has to define it from the left and from the right side so that it works. And she can apply these tools to show that linear order expansions of free homogeneous structures, again here we mean homogeneous structures with free amalgamation in the sense that John checked on, they have simple automorphism groups as well as universal n linear order for n greater or equal than 2. Another generalization has been from Calderoni, Kwiatkowska, and Katrin herself, also last year. I think now it's submitted, it's accepted for publication, so this is 2021, where they don't have a weak stationary independence relation, but a stationary weak independence relation. And this talks about the fusion of two homogeneous structures where one of them carries a stationary independence. And using these generalizations, they show that order and tournament expansions of some very prominent examples, like the rational unison, the random graph, and the random poset, they also have these simple automorphism groups.
Before
so
you
there's a lot of, yes?
Let me ask you a question. In case one of the paper of Kaplan and Simon, there's this old paper of Kekris and Rosendahl about looking at dense conjugacy classes, but that are comeager. Okay.
Yeah.
Because then, okay, that gives you some, let's say, nice information. Do you have any idea if there's any information about not just dense conjugacy classes, but comeager dense?
I think they at least pose some questions. It has been a while since I looked in detail at this paper, but if you want, I can have a look at it and get back to you. I think they definitely think about this. I'm not sure how far the results go in this paper.
Okay, okay, thanks.
Thank you. Yes, exactly. So these are some generalizations to lose the symmetry. And just want to pose some quick further questions, which I'm currently considering with Dugald and Daoud. The first would be, what about, like, we know that with free amalgamation, we have this nice stationary independence. So now if you have strong Frisé limits, which have free amalgamation only for strong substructures, can we just have the same result? Can we give nice characterizations and get a lot of more simple automorphism groups, as this strong Frisé constructions have been used widely? So one example would be the bow tie free graph. Here the tentative answer is yes, like at least for the bow tie free graph, modulo writing down all details. And the second question is, which is like interesting, and at least we're not aware if this is known, what about Hall's group? Like the automorphism group of Hall's group, it's not simple, of course, because it has the inner automorphisms as a normal subgroup. But modulo this very prominent group, is it simple, and can you define a nice stationary independence relation in order to approach this? So it's some outreach. And as you saw from the applications before, it's like a very active area recently. There's a lot of people working around this. And now I want to talk about a recent result with Shaha about polar structures. Yeah, this is here. Exactly. So, okay. And now I'm going to switch to the blackboard green board, which we all missed probably with all the online teaching. I'm sure I think you're also still in online teaching, or are you back at university? Everything's online, right? Online, yeah. So we all missed the green board. So I tried to provide one. And yes, now let's talk about Polish structures. First, we should define what it is. So a Polish structure is a pair consisting of a group G and a set X such that G acts on X. Sorry, it's not only a group, it's a Polish group. Surprise, surprise by the name. Acting on the set X with one important property. Which is the stabilizers of singletons should be closed subgroups. So such that the stabilizers of singletons are closed subgroups. Nice fact, also these pop up naturally a lot in model theory, because if the structure is countable, which we assumed anyway here, then we already know that its automorphism group is Polish. But furthermore, if we let it act on the type space, the space of types over M, then this gives us a Polish structure.
Do you want the set X in general to be compact, or that's just for this example?
No, it doesn't need to be compact in general, as far as I know. Like the definition goes back to a paper by Kropinski from 2010. And I think there it was done generally. Thanks. Now, the question here that we want to consider today is when these Polish structures, specifically arising from first order structure M, are small. So we should define what it means to be small. We say a Polish structure is small. Polish, no, not the German, Polish, the English version. Structure is it's called small. Basically, if there are only countably many orbits on the alpha atom. So if for any n, there are at most countably many orbits on x to the n. Now we also have a notion of a small theory. And we say that a theory T is small. Let's make it colorful. If there are only countably many n types over the empty set. So if for any n, the set of n types consistent with the theory is at most countable. I just want to recall, especially for those not coming from within model theory, a brief part, small part of our world, our universe that we live in. with the definitions that come in handy. It's not the nice one from Gabe's website, but it will serve. So we have, like, we classify our structures in the first order structures due to some complexity notions. And there are many ways. Often, like Shelaf said, the good dividing lines are those which can be defined by many internal and external different notations. So we can define it via properties of formulas or via the number of types and several other things. So I want to focus on 4 classes. The smallest I want to focus on this are the omega stable theories. Which here we'll just say are characterized by having countably many types over countable subsets. Then they are contained in a slightly larger class, which I guess is not often, it's not one of the most studied, but it's the super stable theories. Here I want to use the definition that they are stable and types are always independent over finite subsets. So let's say for every type over whatever set, let's make it realized. Just a second. Being the type of some element over an arbitrary set, there exists a finite subset of the parameters such that the type does not fork. So it's forking independent from its parameter over this finite set, because this characterization we will use. And then the next larger class, which has been studied abundantly, are the stable theories, which have also a lot of different definitions. So here I want to use the one with formulas to also see the different characters of the definitions. So for example, we can say that no formula has the order property. So they cannot order an infinite set. And then it goes on in several directions, but I just want to complete it to the NIP theories, which they're not so important. We'll just mention them as the name, as they appear in the conjecture from the paper of Bischoff from 2010, which says the following. Assume M is countable, which, okay, we already assumed this. And it's also a saturated model. Of its theory, and the theory shall be small, again meaning countably many types over the empty set, and NIP. Further on, let delta be a finite set of formulas. Then the conjecture says, two parts, one stronger than the other, that this polar structure, the automorphism group of M, together with all delta types, which means types that only consist of instances of formulas from delta, is small. And the more general version says that even considering the entire space of types, this is small. Okay, let us recall when these things are trivially true first. So we observe that if M is omega stable, you saw the definition of omega stable we picked where there are only countably many types over countable sets, but M is countable. So if there are only countably many types, there can only be countably many orbits of types. So trivially, 1 and 2 hold. Furthermore, that's a nice exercise. If M is stable, then also 2 holds. Wait, one holds. This was a stricter version. And here you can use exactly the definition we gave. Yeah, like we use that no formula has, like all formulas are stable. If it's not midnight where you are and you want to think about something, you can try to solve the exercise. Let's actually, for our setting, let's make it even more rigid and see if it's true in an even stricter case. So let's narrow the question and say, assume in addition to the above, M is not only NIP, M is stable even. And instead of only being small, let's assume it's omega categorical. So we saw this means it only has finitely many types for overall finite sets, and not only countable. Is the conjecture at least true then, now with these stronger conditions? So is this a small polar structure? It is a fact, also very nice proof, that if we have a omega categorical structure, which is super stable, then indeed it's already omega stable. So there's no proper distinction between super stable and omega stable structures as soon as we look about categorical structures. This means if you want to find a counterexample, so stable structure which is omega categorical and not small, then we need to look for something strictly stable. Now, there's not too much of a choice if you look at strictly stable omega categorical structures. In order to argue this, I want to give a little bit of history. So there's the famous Lachlan's conjecture, from 1974, which says that any stable omega categorical theory should actually be omega stable. So we saw, okay, for super stable this holds, but what about stable? There has been several papers, most importantly one by Turlin, Harrington, and Lachlan, and also another paper by Lachlan independently. But this is at least what Udi refers to in his counterexample, which basically state as a consequence that if we have a stable omega categorical theory, then either it's omega stable or necessarily we can interpret a pseudoplane in it. So a stable omega categorical theory is either omega stable or like it's omega stable if and only if there is no pseudoplane defined interpretable in it. I don't want to go into the definition. It's kind of it's a structure which has points and lines and some incidence conditions between them. But what now Udi did in '88 is he constructed, I'm not sure actually, like I asked him for a paper and he gave me some some handwritten notes. I'm not sure if this has ever been really published, this example, but there's been a lot of work around it where people make an exhibition of this counterexample. He constructed a stable omega categorical, opala, there's something weird with the pen, categorical pseudoplane with a strong Fissé construction. Let's call it P. And by the above, because we know, okay, it cannot be omega stable now because it has a pseudoplane, but it can also not be super stable because then it would be omega stable. So by the above, we know that this is strictly stable. And at least to my knowledge, like the proof that it's strictly stable uses exactly this thing, which is like a very involved paper. To my knowledge, there has not been yet a direct proof that this structure itself is strictly stable, like to just show, to identify some strictly stable types. And now what we did with Schacher is basically, okay, so this is basically the one chance of a counterexample. So whenever you want to see if some properties of omega categorical, omega stable theories generalize to the strictly stable case, try this first and see if it goes or not, and then one can go on. So what we show is actually the conjecture fails for this case already, and even here, even if we stick to one types, we show that this polar structure of depending on the pseudoplane is not small. So there are uncountably many orbits of types over the pseudoplane. And by doing this, we also give a direct proof that it's not super stable. Yeah. Also not super simple, of course. Okay, so let's dive into this part. You said 15 minutes, but we started a bit late until, so I have like 15
Just
more
have
minutes.
like 15 minutes. Or
Okay, cheers. Let's introduce what is pseudoplane. Generally, it arises as a strong Fissé limit. This is why I was bothering you with all the strongness in the beginning. And it's based from the beginning, before doing some modifications, on some initial class, which we will know very well, which is just the class of finite graphs. So maybe let's fix as the language now, the language just consisting of one relation symbol, which is binary and denotes the edge relation. And on this class, he defines a delta function. So whoever's done a bit of Wachowski constructions, there's like always some nice dimensions coming around, which help then forcing very like desired properties into the arising structures. So here we define the delta value of some finite graph A, just to be the cardinality of A, minus alpha times the number of relations in A, where alpha is some real, just for the sake of the construction, we already choose it in the right interval, which is between 3/4 and 1, and A is a finite graph. Okay, so he finds this dimension, this function. We don't know yet if it's a dimension function. And coming from this kind of association of delta value, we can now define this notion of strongness. So let's say that A is strong or closed in B, if and only if the delta does not drop between A and B. So the delta value of A is always less or equal than the delta value of any intermediate structures for all C which are containing A, but that being in B themselves. Okay, and now he argues that for a specific choice of alpha, which in particular it means something of infinite index, meaning it's very, very badly approximatable by rational numbers. depending on this alpha, he defines a function f, which is strictly, well, monotone and unbounded. Which takes input values from the natural numbers and gives back rational numbers. And this function will have control of the dimension of our classes and forces it to be omega categorical. So with the help of this function, he sets class Kf to be a subclass of K0 consisting of all those finite graphs which have the property that all its substructures have a delta value bounded below by the value of this function. And this function is unbounded. And this only depends on the size of A, which means if the structures get large, the delta has to get large. And he shows with the right choices that this is a strong Frese class. And its limit then equals P. He shows that this is stable and it is indeed a pseudoplane. Now we want to study this plane a little bit more. First, we should say what a closure is, which comes from the dimension. So whenever we have a finite subset, you can also always generalize this, but for the sake of this talk, you only need finite things. Then there is a unique smallest subset, which is actually closed. And we call this the closure of A. So it's a subset contained in P such that A is contained in it. And it's strong in P. I will just write it like this. This means strong in all the finite structures in between. This is called the closure. Not always for all kind of dimension functions we get, like for all kind of delta associations, one gets this. One has to have some kind of forbidden infinite decreasing chains to get the closure notion of A in P. And now we want to give a quick argumentation why the resulting structure is indeed omega categorical, which is like a very interesting part. The first thing is that we should kind of remark is that closures determine the type. Meaning if we have two structures, A1 and A2 in P, and a like they're isomorphic, a finite isomorphism between them, then this extends to an isomorphism between their closures if and only if they have the same type. So it extends to an isomorphism between the closure of A1 and A2. If and only if the types are equal. So really everything that matters. Now this is clear because it's a strong Frese limit. We said the limit has the property of being homogeneous for the strongly embedded substructures. And another observation is obviously that the delta value of the closure, because we look at the smallest delta value we could have, it's always bounded from above by the delta value of A itself. And now this is what I already hinted at before. The F condition of the class, meaning that large sets will get large delta values, because the function is decreasing. This now implies that for any A, there is a bound on the size of its closure, depending only on the cardinality of A. Which means now if we have, we consider n types, we have just one relation. So there's only finitely many isomorphism types of these endpoints. And then we know that all the closures are bounded by the size. So they have only finitely many non-isomorphic closures. And in the end, there are only finitely many n types. This is how the proof goes. And hence this condition is exactly so nicely done to force the fact that P is omega categorical. Okay. So this gives us a very small theory. It's omega categorical. There are only finitely many types over all the finite sets. Nevertheless, we want to show now, or to argue, that over the whole structure, there's even uncountably many orbits, not only uncountably many types, uncountably many orbits on them. Okay, what's the idea? Yeah, the idea is that we want to predefine the dimension already now. It's one very important notion whenever we deal with these dimension constructions is the notion of dimension. So for a subset of any model of the plane, we define the dimension of this as being the delta value of its closure, which is uniquely defined. And then we can also say what is the dimension of some tuple over a set, which we just define by being the dimension of the union of both minus the dimension of the base set itself. And coming from this, we get dimension notions for types. So yeah. So if we have any type, let's say, because we only need it for types over the pseudo plane, and we set the dimension of this type to be the infimum of the dimension of any realization over the finite subsets. Okay, so we get a dimension function of types. And clearly, this function D, and I will even restrict it now to one types, because that's all we need in the end, is a function from the type space into the reals, even the non-negative reals. And it's clearly invariant under automorphisms, because the dimension is invariant under automorphisms, the delta value. So all we need to show is that this has an uncountable image. So if you can show that there are types, like for uncountably many different dimensions, we find a type with this dimension, then we know that D cannot be in the same orbit under the automorphism group. Hence, there has to be uncountably many orbits. So that's the idea. Now we just have to find nice dimensions. We have to construct dimensions. Yeah, the corollary of proving this claim would be that the corollary would be theorem some theorem above here, 3.9. Okay, One observation in order to study this uncountable image is that the delta value of any of finite sets, let's say like for all finite sets, the delta value is always natural number minus alpha times natural number, right? Which is countable. But also one can see that for an irrational alpha, this is dense. This is dense in R. So we can build limits. Now fix alpha as above between 3/4 and 1 to get the right construction. And now we can construct a sequence Dn, which will always be of the form some Pn natural number minus alpha times Qn. Pn and Qn in n. Which is completely contained. Wait. Sorry, I forgot something here. Sorry. We wanted to, now we want to show that basically the dimension function is uncountable. So now we fix an arbitrary beta between 0 and 1 minus alpha. So this is obviously an uncountable interval in the reals. So we fix an arbitrary beta. And we construct this sequence Dn because it's dense in the reals. So we construct it such that it is always in the interval between beta and 1 minus alpha. So in particular, larger than beta. And strictly decreasing, such that it converges from above to beta. Of course, we can do this for density reasons. We just always pick one element in beta plus 1 over n, and then we pick a decreasing subsequence. So now I'm almost at the end. What is now the strategy of having a sequence for proving the theorem? We want to construct a like point actually C and sets A and a Bn all in this class Kf with several properties. The first is that these sets are always contained in each other, they form chains. The next one is that An is always closed, a closed subset of Bn. And C is also contained in Bn for all n. And then we want that actually, okay, An is closed, but as soon as we add the point C to An, the whole closure shall be Bn. And then now comes the part which is like the crucial part. We want that the delta value of Bn over An, which then by the property above is the dimension of C over An, is exactly Dn. If we can construct this, and it turns out there's actually a rather nice construction of trees, which is not too hard, playing with long and short paths, then we can afterwards define the infinite set A, which is just the union of all An, and then embed it strongly into the pseudoplane, because they've been all structures of the class. And furthermore, we define the type that we want, the type P, which depends on beta, which is just the union of all the types of C over An, which is consistent. And this will be a one type over A. And we in model theory, we know that we always can pick non-forking extensions. So then we pick a non-forking extension Q, of this type to the entire plane, which means in particular the dimension doesn't drop. So we have, with this construction, two important properties. The dimension of the type Q beta, does not change towards the dimension of the type P beta because it's non-forking, and non-forking can be characterized through the dimension. And this is the infimum of the dimension of C or the AN, but this was just the infimum of the numbers Dn, which is beta, because they converge to beta. So that's nice. And the second property actually also is that Q beta forks over every finite set. Because if it if it doesn't fork over something, it has to be inside A. And there we know that we have like this chain of finite sets, which it always forks. So in particular, it is strictly stable, and that's just the corollary. So the corollary of this construction would be, that's the last part, for any of the truly noted uncountably many beta in 0 and 1 minus alpha, there is some type, and as we saw, it's even strictly stable, which has dimension beta. And this proves the theorem. This proves that we have uncountably many dimensions, and hence two types of different dimensions cannot be in the same orbit under the automorphism group, and hence we have uncountably many orbits of types over the free pseudoplane. I'd stop here. I wanted to do some more small proofs, but it's also late for you, maybe not so much as for me. So yeah, thank you very much for your attention.
Thank you, Isabel. Any questions for Isabel? Or any further questions for Isabel, perhaps?
Yes. If you go to the conjecture again, the original one of Zizek.
Yeah. Oh, voilà. So this is why I didn't do everything on the, yeah.
Yeah. Okay. So for the super stable case, it's known to be true, right? For what the things you said, well, at least, yeah. Okay. So
wait, sorry. Super stable, but you mean omega categorical, not
Countable, yeah. Categorical, yeah.
Yes. Okay. So try strongness on the other side on NIP. If you're, for example, strongly dependent and omega categorical, any clue? So in a sense, there's a rule of, let's say a simple rule that stability is to superstability, but NIP is to strong dependence, more or less. Okay, that's the rule of thumb. So you would say, well, maybe a natural way of trying to prove this in a reasonable setting is use, okay, so it's a small NIP, but assume it's strongly dependent. Yeah, instead of just NIP. And the theory is omega categorical.
Yes, and we're talking about the first part, or?
Oh, yes, exactly. So maybe there's a hope there. So trying to prove the theorem if it's strongly dependent instead of NIP and assume omega categorical, whatever you want. Yeah, any ideas in that direction?
No, we haven't looked into this. I'm not sure if I see the correspondence, because like this is actually true for arbitrary stable theories, not only for super stable.
No, but that's why. So the point is start assuming extra stuff. Yeah.
Yeah.
So a reasonable assumption is change NIP for strong dependent, which is maybe more reasonable. Yeah. I mean, maybe there's a hope there. I don't know. It's just guessing. Yeah.
Yeah, this sounds interesting. I might have a look into it. We were more looking into other questions. So, for example, there is the property that in an omega stable omega categorical theory, whenever you have an infinite sequence, you can pick an indeterminable subsequence. So this is another open question, whether this generalizes to stable theories or not. And like we were more looking, kind of trying to use the example to study further questions, what generalizes in this direction, instead of focusing on the validity of this conjecture. But this is a nice project for future thoughts.
Okay.
Thanks.
Okay. We go with John. I think you raised your hand.
Yeah. Yes. Yeah. Sorry, I'm on a computer that the camera doesn't work. Just one remark, and that is that Herwig has a paper called something like weight in omega stable, finite weight in stable theories, I think, in the JSL in 95. And that he does it by sort of doing Reshofsky construction in a family of finite languages. And then in the infinite language, he gets his counterexample. But the reason I bring this up is that in that paper, he then gives a very nice presentation of Rudi's original construction.
Oh, really? I saw some presentations like by Frank and by David, but I wasn't aware of the paper of Borvik. Awesome, great. Thanks a lot. I'm gonna have a look at this.
And then my question was, in the result about the simplicity for the Reshofsky construction that you stated at the beginning, it was in your list of known results.
Yeah. Oh, this was in the slides. Yeah. Yeah.
Yeah. So just yes. So what do you mean by the Reshofsky ab initio? Do you mean the omega stable case or the strongly minimal case?
The omega stable case.
Oh,
Right.
okay.
There's also. Yeah.
And is anything known about the strongly minimal case? Oh, they aren't LFC. Well, no, we don't.
Strongly minimal, then by Laskar's result already, we know that the automorphism group is simple modulo the automorphism group of bounded strong automorphisms. So there's already the.
That's that comes from what?
Yeah, so,
That comes. Oh yeah,
so
Vanya?
one can prove there is no bounded automorphisms, so that immediately gives simplicity. So in the collapse version, simplicity comes from the Laskar's result, as Isabel said, and then the bounded automorphism you can prove doesn't exist. So you just simplicity comes there for free. But this result there is for rational coefficients. So we cannot actually, we don't have the result for irrational coefficients in the ab initio case.
Well, but the irrational coefficients brings you that's in the stable, the stable, but not omega stable case.
Yes, that's true.
But I thought that Laskar's result was just for the field. Does he have the general result for the?
Yes, yeah, he defines bounded automorphisms also, like in the sense of being closure independent, basically. And no, he gets it generally for strongly minimal theories. With he basically shows that the automorphism group of strong automorphisms is simple modulo the normal subgroup of strong bounded automorphisms, where boundedness comes from the dimension which comes from the strongly minimal geometry.
Okay, thank you.
I actually have a small questions for you. So, I mean, most of the times you were assuming that the theory was small, correct? In order to make these conjectures, but do you know if people have studied, for example, those cases where you have like a very simple structure or a very simple theory to understand that it's not small, say, for example, the everywhere infinite forest or things like that?
If your theory is not small, then you have no chance that the structure will be small because, well, the types over empty set are fixed by an automorphism. So.
Like you would already get uncountably many, like a small means for the theory that you have only countably many types over the empty set. So if it's not small, you only have, you have uncountably many types, but not orbits.
Yeah, you have complementary orbits because these parts over the empty sets are not moved by automorphisms. Yeah.
Okay. But people have described these automorphism groups or not?
Of the everywhere infinite branching.
Yeah, for example.
How do you construct it? Isn't it like, this is what you're saying is like the free pseudospace, Annie, the tree which has infinite branching?
Yes, exactly.
Yeah, so this is a free amalgamation class, so it has a stationary independence, and it's simple because it's a free amalgamation class with a relational structure.
All right. Okay, thanks.
Wait, so it is actually omega categorical, right?
No, you can have
No, because
different and connected components.
Yeah, you can exactly. It depends. Like you have the connected, the prime model, which is connected, and then all kind of copies of connected components.
Yeah. Yeah. I also have a question, if I may. So in this, counterexample, do you have a precise characterization of the orbits? I don't know. Does equality of dimension, for example, imply that the types are conjugate?
We didn't think about this. I don't think it does. I don't think it does. I guess it depends on when this dimension is reached. So, for example, I mean, very trivial thing, dimension 0, which is a realized type. Wait, but it's transitive, so that actually would work. Somehow I don't think it is, because if the dimension that the type has, maybe like there can also be stable types, is witnessed over non-isomorphic sets, then I don't think there can be an automorphism sending one type to the other, even though they have the same dimension.
Yeah, right. This seems way too naive. But on the other hand, like intuitively, there should be some nice classification of orbits, because you have this Sherlock's result that over large models, you don't get many more orbits. So perhaps there is some reason for it. But
yeah, maybe for the. So I guess for the super stable types, we get this smallest subset where it's independent over, which is finite. So probably there you can just say, okay, types are in the same orbit if they're independent over isomorphic subsets. I don't know if this is but for the stable types, I don't know. It must be more than what I mentioned. But
yeah, it looks like it definitely must be more. Yeah. Okay, thanks.
Okay. One last question for Isabel, perhaps? Well, if there are more questions, then thank you, Isabel, again for your talk, and thank you everyone for coming to this semester of Seminario Flotante. We're gonna take a break. This is the last talk of the semester, and we'll be back probably in August, let's say. So it has been a pleasure to have you all here.
Yes, thank you very much to all of you who participated in the seminar, and to Dario for being on board with co-organizing this with me. Thank you very much. Thanks a lot, Isabel.
Thank you very much for having me and for all the questions. It's a very nice interactive seminar. Should drop by more often.